have a lot of so regarding differential equations, we have an expression which is dy over dt. This can be equal to ky, okay? So if this is an equation, the solution, it's always equal to y is equal to y0 e to the power kt, okay? This is the general solution, which means that if we have, for example, dy over dt equal to minus y, this means that y is equal to y0 e to the power minus t, okay? So we just substitute for k, that's it. If we have another differential equation, which looks like dy over dt equal to 3y, then y is equal to y0 e to the power 3t. y0, it is the initial value of the y, okay? So if we start from some specific value, the quantities, they exponentially increase or exponentially decrease if the general expression is given like this. Sometimes the differential equations or the quantities or the rate of change of the quantities, they don't depend only on one variable. So if it is something like this, it's going to be relatively easy. And by the way, how can we solve this one? We solve this equation. So you take this for granted or you do the following. We can write this one as delta y over delta t. This is equal to ky. And then delta y divided by y is equal to k times delta t. Then we integrate both sides of the equation, and this delta y, it's better if we write this back as it was. This is k dt. Now, the integral of y, this is natural logarithm of y, and this is kt plus some constant c, because the integral and the differential, they are inverse functions of each other. So that's why we get kt. And then we take the exponential of both sides of the equation. So we get here e to the power ln y. This is equal to e to the power kt times e to the power c. E to the power ln y, they are inverse functions of each other again. So we simply get that y is equal to e to the power c times e to the power kt. So somehow we proved that this expression is correct because this is what we obtained, okay? Now, can you find a differential equation or anything that you might pick from the book? You want me to find one? Non-picked it. Okay. What page is it from the book? I'm afraid I might have solved this one in the other section, so I might choose not to solve 9.8 if we've done it before. Okay. Problem 9.8. It should take me not much. Application of diagonalization, problem 9.8. You know, this looks to me like I've solved this one before. 310. Alisa, what if I do 9.7? Because I think... okay, thanks. Let's do this. So we have the problem 9.7 on page 310. Okay. So here we have page 310, problem 9.7. And now we have two variables, and the rate of change of these variables is given. And we see that those two variables are coupled with respect to each other. So we have the derivative of y1. So we can denote this one as dy1 over t. This is equal to y1 plus 4y2. So you can have a look also. y1 plus 4y2. And the second derivative of dy2 over dt. So this is dy2 over dt. This is equal to 3,2. Okay, this is 3y1 plus 2y2. Okay, then here we have, as we see, we have a rate of change of two variables, but that they are not as simple as these examples because they depend. We have two quantities which are coupled. Okay, so So let's write this here. So these are coupled variables. Okay, so these are coupled variables, which means that y depends on y2 and immediately y2 affects y1. Now, in order to solve this problem, it is going to be much simpler. And let's see if we have initial conditions. It looks like initial conditions are 1, 0. That's good. So initial conditions, we start from 1, 0 at t equal to 0. So at initial time, these are the values that we are going to have. That's good. So now the derivative, let's denote dy over dt. Let's denote this one as y dot, as this becomes a little simpler. Now let me take this away, this information away, and let's try to remind us each other regarding our language that we have used so far. Okay, let's assume that we have a standard basis where we have two variables, x and y. Okay, this is standard basis. Then we have a better basis. In this basis, we have two variables, which are u and v. Okay, so sorry, this is x and y. Let's call this one y1 and y2. Apologies, y1, y2. U and v are the two variables. Now, in this standard basis, these variables are coupled. We want to decouple, so we want to go to a new basis. And when we say that the variables are decoupled, that means that u should depend only on u, and v should depend only on v. So if we move in this better basis, we are not going to solve these equations, but we're going to solve these, okay, which are relatively easy. They are very easy. Once we diagonalize the system, or once, as we see here, depends only on y. We don't have a z or x. But how can we do it? We know how to do it because we can diagonalize the coefficient matrix. The coefficient matrix, so this whole system, let's look at the equation as a whole. This equation as a whole, this can be written as y1 dot, y2 dot, this is equal to 1, 4, 3, 2. That's good, times y1, y2. This system, it is coupled. And the bad thing about this system is that the off-diagonal terms are non-zero. We don't like this, okay? We like the off-diagonal terms to be 0. How can we do it? We need to diagonalize this matrix. So this is the matrix A. Then for this matrix A, we have to solve this fast. So let's leave this one for a while so we get used to this expression. And to diagonalize this matrix, we need to find lambda 1 and lambda 2. How can we get it? Let's see that lambda 1 plus lambda 2 is equal to what? Who can help us here? Should be equal to 3 because they are equal to the trace of that matrix. And then lambda 1 times lambda 2 should be equal to the determinant. What is the determinant? 2 minus 12. What is it? It's minus 10, right? This is minus 10. So if this is minus 10, then what could be a good pair of numbers which satisfy this condition? There could be 5 and minus 2, okay? Because 5 minus 2 is 3, 5 times minus 2 is minus 10. That's good. So we found two lambdas. So we have lambda 1 is 5. So then this means that here we can write the diagonalized matrix, which is minus 2, 0, 0, 5. We got it, okay? In the new basis, this is how this u's will be coupled. So immediately we can say that the rate of change in u, so let's write this u dot, and the rate of change of v dot, this is going to be equal عم تجونت?
Oh.
Okay, sorry. I just had an internet fluctuation, but everything, it took some time. Sorry about that. So let's continue. So it looks like just by looking at the trace and the determinant, trace and determinant of a 2 by 2 matrix, we found the two eigenvalues, okay, 5 and minus 2. If these are 5 and minus 2, that means that in the standard basis, we had y1, y2. In the better basis, we have u and v. So this is a vector now, okay? And this is also a vector. And let's not forget that we had initial conditions, which were 1 and 0, right? And we need to know what is initial condition in this new basis. So initially, y1 was only a value of 1, y2 was 0. We need to see what is this u0 here. So the general schema that we're going to use is the following. Let me use this section here. Maybe it's better if we do it here because we have the sets here. So the general schema is the following. We are given a value of x0. Using x0, we can find the u0, which is the initial condition as seen from the better basis. How can we move from x0 to u0? We move with p inverse, right? Because during the whole second part of the semester, so wait a second. So we used to say that we move this way with matrix P, right? And we move backwards with P inverse. So then x0, we multiply x0 with P inverse, we get u0. Then we get ut by multiplying with diagonal matrix to the power t. Then we move and find xt. So the question for us is this. We need to find this. And we can also find the same xt using this path. How do we do this? We can write the following. We can say that the xt is equal to a to the power t times x0. But this is more difficult, and the better way is to transfer this problem to the better basis, solve it here, and bring it back. That's it. Okay, so this is the traditional path that we need to take. Now, what should we do next? Next, we need to carefully determine what is P and P inverse. So how can we do it? So let me erase this one for a moment. So this is a general picture. We're looking for P. Let's pick up the first eigenvalue, which is minus 2, which means that we have 1 minus 2 minus 1, 4, 3, 4. No, this is wrong. 2. Is this correct? No, this is, sorry. This is 1 minus minus 2. This is 3. Okay, so that we don't miss this, we're picking up this one from here. We multiply with AB, and this should be equal to 0, 0. So what is a pair of A and B that can satisfy this condition? So the first equation, we get 3A is equal to minus 4B. Okay, then A can be minus 4, B is 3. This is minus 4, B is 3. You can check this one. 3 times minus 4 minus 12 is equal to minus 12. That's good. The other equation, so this one, this corresponds for an eigenvalue of minus 2. Now, similarly, for an eigenvalue of 5, we have the following. 1 minus 5, this is minus 4. This is 4. This is 3. And 2 minus 5, it's equal to minus 3, okay? Then similarly, we multiply with AB, and this should be equal to 0, 0. So what is the equation that we get here? We find that A is equal to B, right? So here we can put 1, 1. That's good. We found the matrix P. Now that we found the matrix P, we know matrix D, then we need to determine P inverse. What is P inverse? What is the determinant of P? Any idea what is the determinant of P? First of all, this is correct. Yeah. So this is minus 4, minus 3. It looks like minus 7. Minus 1 divided by 7 times, this is 1, minus 4, minus 1, minus 3. Okay. So this is what the P inverse appears to be. then we need to use the board a little more efficiently. But okay, so let's take this away, because now we know how we can solve these simple differential equations. And it looks like P inverse, I can try to write this again. P inverse is equal to, let's have here 1/7 times, we put the -1 inside, this becomes -1, 1, 3, and 4. Is this correct? Can you check here if we made any mistake? This is -1. If we multiply this row with this column, what do we get? 4 plus 3, 7 divided by 7, 1. That is true. So this is 0. This is 0. And then we get also 3 plus 4. That's correct. So P times P inverse, they are equal to identity matrix. So we have now what we need. We were given A. Okay, we were given A. What did we find? We found D, P, and P inverse. So here we have all three of those. P inverse, D. Good. So now let's follow. So we found all the matrices. Then let's find what is U0. U0, it's equal to P inverse times X0. So let's write this one here. Well, let's write it here. U0, it's equal to P inverse times X0, which is equal to 1/7 times -1, 1, 3, 4 times the initial condition, which was 1, 0, right? The initial condition, we have written it here. So what is this? This is 1 divided by 7 times, this is 1/7 times -1, and here we have 3. Okay, this is the initial condition. -1, 3 divided by 7. Let's write it here. -1, 3 divided by 7 times 1/7. Okay, so we found U0. That is good. Now that we know U0, we should get what is UT. Okay, so now UT, it should be equal to D to the power T times U0. Wait a second. No, I'm wrong. I am completely wrong, because no, that's not true. We just need to find this. U0, we found it, that's correct. Now, we want to write the same pair of differential equations like this. So, this is this one, right? This is transformed like this. Then let me write this in this part. We can preserve some symmetry of the board. So what is the first, or let's write it here. The first differential equation that we obtain from here is that, what is U prime? U prime, it's equal to -2U. I almost made a mistake. And here we have V prime, or the first derivative of V with respect to time, is equal to 5V. Now, actually, we were given this system of equations. Probably it's best if we write this one y1 prime, okay? So this is the derivative. This is y1 prime is equal to here. Let's make this a little more elegant. And this is y2 prime is equal to this. Now, it is very clear that this system of equation and this one, they are equivalent, but this is way simpler, right? So since this one is way simpler, we can say that U is equal to U0 times e to the power -2t, okay? Because we know how to solve this differential equation. And then V is equal to V0 e to the power 5t, okay? Now, we solved this differential equation, and it was very simple. We're in this domain, okay? So this is the solution. Now, we need to find, so this is the general solution. We can apply also the initial conditions. The initial conditions here, actually, we will substitute, instead of U0, we'll substitute -1/7. So U here, it's equal to -1/7, yes, this is -1/7, times e to the power -2t, okay? And V as a variable, this is equal to 3/7, or 3/7 of e to the power 5t. So you see, we could easily solve this system in the new basis. Then, okay, so we didn't make any big mistake. Now we need to find how the vector y1 and y2 depend on u and v. Now, y1, y2, how do we do the linear transformation of one vector from this basis to this? We can do it by multiplying by the matrix P, you see? So we move the linear transformation of vectors from here to here. We do them through P. Then P is minus 4, 3, minus 4, 3, 1, 1. And these we multiply with UV, right? So what is UV? This is the general expression. Instead of U and V, let's write this. This is minus 1 over 7. Minus 1 over 7 e to the power minus 2t. And here we have 3 over 7 e to the power 5t. Okay, and y1 and y2, finally, they would be equal to, we have here minus 4 times minus 1 over 7. We get here 4 over 7 times e to the power minus 2t plus 3 over 7 times e to the power 5t. Okay, this is, let me erase this one. This is y1. And then y2 is equal to minus 3 over 7. Let me write this a little better. Minus 3 over 7 e to the power 2t plus 3 over 7 e to the power 5t. Okay, we solved this one. So it looks like, how does y1 and y2 change as a function of time? They can be seen here. So it looks like y1 and y2, depending on the dynamics of the system, will exponentially decrease with a coefficient of minus 2 as a function of time, times 4/7, plus an exponential increase of e to the power 5t as a function of time, times 3/7. Okay, and then y2 it's composed of an exponentially decreasing function plus an exponentially increasing function. They are not the same. This is increasing much faster than the decrease of this one, but the mixing of the parameters is this. The solution is this one. Any question? Okay, if you have no question, let's give another